get asymptotes then. Okay, so we've already talked about asymptotes. We haven't done much with oblique asymptotes yet, so I'm going to go through that a little bit. So just kind of to review, first of all, let's just kind of write down an example of each one. Okay, so for instance, we've already learned if you have this is a rational function. So if you had something like, say, f of x is equal to, let's say, 2x squared minus x over 3x squared plus x plus 1. Just write that down, okay? What is the horizontal asymptote on that one? 2/3, okay? Because if the degree of the top and the degree of the top are the same, then your answer is right here. So that's what your asymptote is. We've already talked about that, so that horizontal asymptote is y equals 2/3, okay? And that was something that's important when we were talking about limits. And then the next thing is, if you had this, if you had, for the example, say you have x plus 1 over x squared plus, say, 3x plus 5, that's another example. Okay, what's the asymptote on that, the horizontal asymptote? 0, y equals 0, okay, because the degree of the top being the, first power, degree of the bottom is the 2. Anytime that the degree of the top is less than the degree of the bottom, then you get y equals 0. So we've talked about that. Okay, that's nothing new to you. But what happens is if the degree of the numerator is greater than the degree of the denominator, then you don't have a horizontal asymptote. So you might have an oblique asymptote. What an oblique asymptote means is if the degree of the numerator is 1 bigger, then you get what's called an oblique asymptote. Now that's just like a line that's slant. So let's write an example down for this. Let's say we have f of x, and let's say you have x to the third plus 1 over x to the second plus x plus 2, or something like that, okay? Now the thing on this, to have an oblique asymptote, they have to be off by 1, okay? If that was a 4th power instead of a 3rd power, then you would have an asymptote that's actually a parabola, which is kind of weird, but you could have that. So what you would have there is it would just be a line. Now you can find that line. We're not going to do too much with that in this class, but you could do a division problem and you could figure out what that oblique asymptote is, but the point is that is a linear function. Okay, that's the idea. So we're going to look at that a little bit to finish up this section then, okay? So let's give 2 examples. I already gave you one. Something that's got an oblique asymptote. Okay, so let's just write a couple of things down. So let's say you had x squared minus 2x plus 5 in the numerator. What would the degree of the bottom have to be in order for it to have an oblique asymptote? X to the first, right? You would have to have x to the first, okay? So those things have to be different. You could just have x. That's good enough. You could have another number in if you wanted to, but that would be an example of something with an oblique asymptote. Okay, get your calculator out, and I want to have you graph this, and this will help you see this, I think, hopefully, anyway. Okay, so let's put in the example I just made up, and what you want to do is you want to put in parentheses, you want to put the numerator in. It's important that that is in parentheses, so we have that, like that. Then you want to divide by, and then you want to do the denominator just as x plus 2. Now we're just going to graph this in a standard window. So once you get that put in, you can just go zoom 6, and I want you to just get an idea of what's happening on this graph. Okay? All right. Now if you look at this graph, I don't know where the other part of it is. There should be another part of it. Let's actually do one thing on this. Okay? Let's go zoom, and then go 3. Zoom out 3. Okay, just type zoom, then 3, then press enter. There we go. You'll have 2 parts of this. Okay, so what I want you guys to see is, as you go to infinity, what's the graph doing? It's going to infinity also, isn't it? So if you're going infinitely this way, the graph's going that way. But can you kind of see how it just follows a line? Okay, yeah, there's a line there. So actually you could find that oblique asymptote and it would just be a line. Same thing happens here. If you're going infinitely to the left, the graph's going infinitely down. That's called an oblique asymptote. And it's going to be a line that does that then, okay? All right, here's one other illustration. Let's say we have g of x. Now I'm going to do, with this one, let's say we have like x to the fourth minus 2. Well, what would the denominator have to have in it? X to the third. Now, it doesn't matter what else it has, but that would be another example. If you graphed it, you would see a line on that. Okay, so I do want to graph this one also. And this one may be a little bit easier to interpret anyway. So if you put this in, you'd have to have the numerator in a set of parentheses. So you'd have x to the fourth and then minus 2. And then just divide by x to the third, and then just take this back to, whoops. Yeah, come on, just pressed the wrong thing. So we want to put in x to the third. And then just go standard window. So again, once you got that put in, you should just go zoom 6. Okay, and then you'll get a graph that looks a lot like the one we just did. So you guys see what I'm talking about? Okay, there's going to be a line there that goes through like this. Okay, now what would happen on this one is that line would give the asymptote like that. All right, is that clear with everybody? Okay, anytime that the degree of the top is 1 bigger than the bottom, that's what your graph's going to look like. It's going to have an oblique asymptote in it. Okay, so what we do with finding an oblique asymptote, we're going to kind of limit how far we go with this in this class. But if you want to find an oblique asymptote, really what you do is you do the limit of the function I'm giving you as x goes to infinity. So we're going to do the limit of x plus 1 over x. Okay, now we're just going to focus just on this for now. Okay, now let's do the limit laws that we learned. We learned that if you have a limit of a sum, then you can do the sum of the limits. So I can write that as limit x goes to infinity of x plus limit x goes into infinity of 1 over x. Okay, that's what we got to figure out. So let's see if we remember anything about this or not. Well, what would happen if you did 1 over infinity? What do you get? That goes to 0, right? This thing right here goes to 0. Okay? Now what's going to happen on this then is if you take this and you plug that in for infinity, that just goes to infinity like that. So what would happen, so if you just have x going to infinity, if you just replace x with infinity, it just goes to infinity, right? But this one goes to 0. So what you really get is you really get this limit right here would just go to x, but that would go to 0. So the oblique asymptote is y equals x. Now what's going to happen on this is this one defines what that line is. This one goes to 0. Remember, this is real important. We've talked about this. Anytime you do a limit, and you got to either be going to infinity or negative infinity of a constant. C is just a number, and that number could be a trillion, or it could be a Google. You guys know what a Google is? Well, that's a super big number, okay? But my point is, as long as that's finite, and this thing right here, that's going to go to 0. Always, because that denominator is going to be infinitely bigger than the numerator, so that goes to 0. Okay, so let me show you what this looks like on the calculator. Okay, let's do this couple of more things with the calculator. So what I want you to do on this is put in the function I gave you. So it's just x plus 1 over x, like that, and then just graph it in a standard window. So just go zoom 6. And you'll get something that looks like the other examples I did. Now the other thing I want you to do is I want you to put in y equals x. And this will help you see this, I think, real clearly on this example. So just go to y2 and put in x. And then go ahead and graph that. Just regraph that. And what you're going to have is you're going to have your function. See what's happening? You see what's happening is as you go to infinity, the graph is getting close to the line. Does that make sense? Yeah? Okay. All right. That's the idea.
So finding the asymptote, yeah, just kind of like a refresher from last class, you
Yep.
plug in infinity.
Yeah, you're doing the limit as x goes to infinity.
When you're finding asymptotes, it's a limit to infinity.
Right. Right, and that's what horizontal or oblique asymptotes do. They tell you how the graph behaves when you're going to infinity or negative infinity. Okay, that's the idea. So the idea would be that they just get closer and closer to each other. Okay. All right, let's do the next one. It's the same idea, pretty much. What you want to do on this is you want to go ahead and do the limit as x goes to infinity of negative 3x minus 1 over x squared. Okay, now you can do this in your head, but what you're really doing technically is by using the limit laws we learned, you're really doing the limit as x goes to infinity of negative 3x minus, and then a second limit as x goes to infinity of 1 over x squared. Okay, that's what you got to know. Now, what happens to this one? You're really going 1 over infinity squared. Where does that go?
0.
So it goes to 0, right? Okay, the denominator is infinite, so that goes to 0. This one right here, let's just go into infinity. Okay, it doesn't matter that you're multiplying it by negative 3. It's still an infinite number. Okay, so what you're going to end up having on this one then is the value of this limit really is just going to be negative 3x minus 0. And to see what happens on that is you're expecting this first part to go to infinity. This part's going to 0. So that means your oblique asymptote is y equals negative 3x. That's it. So really you can do these in your head. All you got to do is just say, okay, that one goes to 0. So there is your asymptote. You see what I mean? Okay, same thing here. That one goes to 0. There's your asymptote. You can do that in your head. Okay, but you need to understand the technicality behind that. So let's put this one in the graphing calculator also. And I think probably by now, hopefully you got the point behind this, but I want to just kind of show you a few little differences. So this one you have negative 3x and then plus, no, it's minus, isn't it? So it's minus 1 divided by x to the second. And then go ahead and y2 and put in our answer for our oblique asymptote was negative 3x. Okay, now you'll get a similar looking graph. Once you kind of catch on to this, you're going to kind of know what the graphs are going to begin to look like. So here comes your function. That's a little different this time. Okay, but same thing, right? So as you're going infinitely to the left, the graph is kind of matching the asymptote. Now why is the line slanting down this time? So it's a negative slope, right? Okay, that's the idea. Okay, so you can have a slant asymptote or oblique asymptote slanting either way. All right, any questions so far? Okay. All right, now this one, what we want to do on this one is something a little different. And this one, first of all, why does it have an oblique asymptote?
Because it's a higher power on top.
Right, and it's bigger by 1, right? The degree of the top's 2, degree of the bottom's 1. So there is an oblique asymptote. So to find that asymptote, here's what I want you to do. You can take this and split this fraction up into this. Negative 2x squared over x to the first plus x over x and then 1 over x. You don't have to have that first power. I'm just doing that to emphasize something mainly. Okay? So what you would have then is you would have, what is this thing reduced to, the first thing? Negative 2x, good. Okay, how about the second thing? 1. Okay, and then the next thing, nothing. It's just the same. It's already simplified. Okay, so what we're going to do now is we're going to do our limit. And I'm not going to do the limit laws this time because you'll kind of, I think, catch on to this where you just do this in your head. So if you're going to do the limit of that, okay, which part of this limit goes to 0 when x goes to infinity? That part, okay? So what's going to happen is that's going to go to 0. That right there is going to be your oblique asymptote, okay? Because that's just when x goes to infinity, it's just going to follow that linear function. So that means your oblique asymptote is just going to be negative 2x plus 1. So you get y equals negative 2x plus 1, okay? All right, let's put this in the calculator. Let's do a graph, actually record a graph on this one. And then we'll kind of look at, one of the reasons you learn this is because of average cost in economics follows oblique asymptotes sometimes. So let's see, just put in the original problem. So I'm going to put in the numerator negative 2x squared, and then plus x, plus 1, and then close parentheses, and then divide by x. So that's what you're going to graph. And then you want to go ahead and do the oblique asymptote, negative 2x plus 1. Okay, let me ask you a couple questions about this. What is the significance of that 1 in this oblique asymptote? That's a y-intercept, right? What is the negative 2?
Slope.
It's going to tell you you're going down 2 over 1, right? So you're going to have a line that's sloping down. Okay, just do it in a standard window, so you can go zoom 6. And then I want you to draw the line perfectly. I want you to have an accurate graph of the line, and then the rest of it will just kind of wing it, okay? All right, let's go ahead and graph the line. You don't need your calculator for this. What you do on that is you would put let me zoom on that just a little bit. Okay, you would go y-intercept of 1. You would go down 2 over 1, and then connect that, and then that'll give you your oblique asymptote, and that'll give you kind of a good picture of that and everything. So there's your oblique asymptote. Okay. All right. When you draw an oblique asymptote, kind of use dashed lines like you do any asymptote. And then the rest of it, just wing it. Okay. It looks like this graph goes through 0, 1, and then it does sort of go up to the axis like this. Then it just approaches the asymptote. And then it looks like you have a point kind of in there somewhere. It goes straight down to the y-axis. Then it does that. So the important thing on this is as the graph goes further to the right and further to the left, what happens? It just gets closer to that asymptote. Okay, that's the idea. Okay, does that make sense? Okay, that's how oblique asymptotes work, and what they are is they're just lines. Okay, so you're going to do that. And you'll be able to do some of these problems in your homework very easily in your head. So for instance, if you had, say you had 3x plus 1 over x. Okay, what is the oblique asymptote on that problem in your head?
3x.
3x, y equals 3x, see? Okay, it's because you got that thing going to 0. You want to catch on to that, make sure you can do that quickly and efficiently. Okay, we've talked about average cost before, so we're going to go ahead and work with an average cost, and then just do a couple of more things with asymptotes and then one application. Okay, how do you find average cost? If I give you a cost function, what do? You divide by x, exactly. Here's your formula right here. You're dividing by the production level. X is the level, the number of things you're producing, so we call that the production level. So if you want to find C bar of x in this problem, what you're going to do is divide this whole thing by x. Okay, so let's just write that as 7,500 plus 65x plus 0.01x squared all over x. Okay, now, okay, why does this have an oblique asymptote? The degree of the top is 1 bigger than the degree of the bottom, right? Okay. That tells you that you know you have an oblique asymptote because of that. So let's go ahead and just do this. Now we'll just do this in our head. You can go ahead and break this up into 7,500 over x plus 65x over x and then plus 0.01x squared over x like that. So if you want to find the oblique asymptote, you want to go ahead and just work that out. Okay? So let's simplify this then. So this is going to be 7,500 over x. The middle one, the x's are going to cross out, leaving you 65. What's the last one just going to be? Now, one of the x's crosses out. So that is your average cost function right there. Okay? Now, can you tell me what the oblique asymptote is in your head?
65 plus 2.
Okay? Remember, the thing is, this one goes to 0, right? That goes to 0. Everything else stays the same. The limit of a constant is a constant. That's 65. That's going to stay 65. That one, if x is infinite, it's just going to stay with that point right there. So that means right here, what's left over is your oblique asymptote. So you'll have, for your answer, y equals 0.01x plus 65. What is the 65?
The
Y-intercept. Slope is 0.01. Okay, so that would be a line sloping up with a y-intercept of 65. That's the idea, okay? Okay, you guys go ahead and do the next one. It's almost like the same problem I did, but just to make sure you're on track with it, I want you to go ahead and give me the cost function and then give me the oblique asymptote. Okay, you can do the oblique asymptote in your head once you get that cost function put together then. Okay. Now once you catch on to this, you can do this in your head. Have you got an answer yet? What? There you go, 0.4x plus 340. Okay. All right. So yeah. Okay. So your average cost function, you're just going to take the whole thing and divide it by x. And you can simplify this in your head. Because you can kind of split that up into the pieces in your head if you want to. And if you did that, you would have 120,000 over x. The x's would cross out there, leaving you plus 340. And then one of the x's would cross out there, giving you that, right? Okay, which part goes to 0? Yeah, the first part. Okay, so this part, when you're doing the limit, that's going to go to 0. That right there, what's left over is your oblique asymptote. So your answer would be, it doesn't matter what order you put this in. I like to put it in mx plus b form, putting the x first, so that should be your answer. Okay? So if you graphed that, you would see when x goes to infinity, it's following that line right there. It's getting close to that line. Okay? All right, does anybody have a question about anything I'm talking about so far? Okay. Okay, let's put this kind of together in one problem here that does this for us. Okay, so I'm giving you on this problem here a cost function. So we're going to find the average cost function. So how do you find an average cost function? Divide by x. Good. Okay, so we got c bar of x. That's the notation. Okay, so we're going to take that function. You want to just write the function, and you want to divide it by x. Okay, now I'm going to go ahead and break it up and everything and do that. And you're more than welcome to do this all in your head if you want to. With practice, that's pretty easy to do. So just split it up like that, and then that would give you the answer to your, the simplified answer to your average cost function is 500 over x plus 2, with the x's crossing out, and then plus 0.2x like that. Okay, so that is your average cost function. Okay, you can even write the answer that way too. They're both the same answer. This is just better to go this far so you can find the oblique asymptote and so you can find the marginal cost. It's easier to work with it in this form. Okay, so let's go ahead and do C. Okay, so what is the oblique asymptote just in your head?
0.2x plus 2.
0.2x plus 2, because this thing again right here goes to 0. You're doing the limit as x goes to infinity. So the answer to the oblique asymptote is y equals 0.2x plus 2. Okay? All right, that's what we've been working on. Now, how do you find a marginal cost function?
The derivative of the average cost.
Now, this says marginal cost, okay? So you do the derivative of the cost function. It doesn't say do the marginal average cost. If you were doing marginal average cost, then you would do the derivative of this, okay? So this should be a pretty simple derivative. Go ahead and do the derivative of the cost function. You can do that in your head. What is that?
2 plus 0.4.
Okay. Derivative of 500 is 0. So we're just going to say c prime of x. Okay, the derivative of that is 0. Derivative of 2x is 2. This is a power rule there, so that's 0.2 times 2x. So you would end up getting 2 plus, and that would be 0.4x like that. That's a power rule. Okay. All right, everybody okay there? Okay, remember marginal is giving you a rate of change, therefore you're getting derivative. Okay, so what we want to do is we want to go ahead and we're going to do this on the calculator. We don't want to do this by hand. Let's go ahead and put two things in our calculator. So what the problem says to do is it says to graph the average cost function. So you can put it, I'm just going to put it in like this, or you could even put it in just like this. It's your call. I'm just going to put it in as this way, 500 over x, and then plus 2, and then plus 0.2x. So we want to get that graphed. Then what we want to do on this is we want to graph the marginal cost. So you want to put the answer to part B in there. So that's 2 plus 0.4x, like that. And then we also want to put the asymptote in there. Now see, the asymptote and marginal cost are pretty close, aren't they? That's part of what I'm trying to show you on this problem. So we have 0.2x plus 2. So you want to get those three things graphed. You want to get your average cost, your marginal cost, and your oblique asymptote in there. Okay? And then let's do this. As far as a window, let's see, I didn't really give you anything to graph this by. Let's start with just a zoom 6, a standard window, but there's a couple of things we're going to need to adjust. Okay, there's your first thing is you'll have your function, and you're going to have, I'll see the function, you're not even seeing it. What I'm seeing right now, I think, is possibly, I think the function's missing on that one. Now what I'm going to do on this is adjust the window out a little bit. Now when we do the window, we want x-min to be 0 because that's a production. Okay, it's got to be a positive number. Now let's take that out a little bit bigger. I'm just going to take kind of an educated guess here. Okay, I don't think I give you a domain on this, do I? Okay, so let's go to like 100 and maybe scale that by 10. Okay, now if you want to figure out your y, what we want to do on this is I like to go to my table to kind of look at how the y values look. So I'm going to go second graph, open up my table. Now see what the table is showing you right now is this is your average cost. That's what that is. This is your marginal cost, so that's given a rate of change of the cost, and then that's your oblique asymptote like that. So it looks like a pretty good thing to do is it looks like the graph starts pretty high. Like notice at 1 you're at 500 and something, and it's going down, so your function's going to go down. So let's try to do something like this and see if this is pretty logical. Let's try to go 0 to 100. Let's go for y. Let's go 0, and let's go to 500. And then maybe scale that by 100 like that. Okay, let's just kind of see what that looks like. Okay, so if you put that in, then you should have a pretty good graph. Where did that thing go? There it is. Okay, so you can get that window set up if you want to. Okay, then I'm going to graph it. Okay, that's your average cost, the thing that's going down like that. Those are your two, and then the marginal is, and the asymptote are pretty close to each other, aren't they? Now what's going to happen on this is the marginal cost and the oblique asymptote are pretty close, so this marginal cost is a pretty good estimation until you get way, way out there because it's got a bigger slope. The difference on these two things is the slopes are different, right? So that's the idea. Okay, so let's do just kind of a real quick graph. I want you to put draw a little graph on here for a second. So let's just kind of draw something kind of like that. And let's label that we had this going all the way out to 100. So we can just kind of do something like that. We're just going to kind of sketch it anyway. And then we have the y going up to 500. And this is going to be cost. I'll make that go 250. That's probably good enough for what we're going to do. And then let's just kind of sketch this. What I'm going to do on this is, to help me a little bit, I'm going to go ahead and graph this and then just kind of draw the shape in like this. Okay, it doesn't have to be accurate. I just want you to kind of have a record of how this goes. So it's doing something kind of like this. Now that graph is increasing. Okay, it's not going to level off because you do have a oblique asymptote, so it's going to get bigger and bigger. you're going to have what we call a minimum average cost in there, okay? Because that does have an oblique asymptote, so that's going to be getting a little bigger like that. And then let's just put in, let's just estimate this. It doesn't make that much difference for what we're going to do. So let's just put in like the line. Now see, that's supposed to have a y-intercept of 2 right there, and then that oblique asymptote. That's not a very good graph, but the idea is as you go to infinity, what's happening to the average cost and the asymptote? They're just about the same, aren't they? Okay, so that's probably good enough. I want you to see that the asymptote and the marginal cost are pretty close, and they're close until you get out to infinity. That's when they start kind of dispersing because the slopes are different. Okay, does that make any sense? Okay, all right, let's do the minimum average cost with calculus, and then we'll kind of talk about a little bit more on that oblique asymptote. So what we want to do is we want to write down the average cost. Now I'm going to write this down like this. Instead of saying 500 over x, let's write that as 500x to the negative 1 plus 0.02x. And that's because that's the form you want that in if you're having a derivative. Okay, so what you want to do to find this minimum, well, what do we want to do? We want to take the derivative, set it to 0, do a little sign chart, and kind of take it from there then. So let's do c bar prime of x. So when you do that derivative, this is power rule. So you're going to have negative 500, x to the negative 2. The derivative of 2 is 0. What's the derivative of 0.2x? Okay, 0.2. Okay, so that's your derivative. Now let's go ahead and write this as negative 500 over x squared plus 0.2. Okay, so what we want to do on that is we want to analyze that, set that equal to 0, and then we want to make a sign chart on that. Okay, so if you set this equal to 0, you'll have negative 500 over x squared plus 0.2, and we probably don't even need to do a sign chart because we already got a graph. Okay, I'll just show you what the sign chart would give. So set that equal to 0. Now if you solve this, there's a lot of ways to do this. One way is just to get the x on one side, choose the side you want the x on. I'm going to just move that over, leave the 0.2 where it is, and then when I move that, that's going to make that a positive 500. Okay, now you have an equation with a fraction in it, so your goal when you solve this equation is just make the fraction go away. So we're going to multiply both sides by x squared. So that's going to leave us with 0.2x squared equals 500. Now how do you finish solving an equation like that?
Divide by 0.2.
Divide by 0.2 and then what?
Square
root. Good. You got to do a square root. Okay. And this is just kind of the algebra involved in here then. So we have x squared equals, then you can take, if you want to, on your calculator and take 500 divided by 0.2, then you can take the square root. That'll give us the minimum average cost. Okay, so that looks like that is 2,500. You can square root both sides. And I think that is, what, 500?
50.
No, 50, isn't it? Yeah, 50 times 50. Yeah, okay. So that'll give 50. Okay. Now, if you look at your graph, that's what was happening, is that's where your minimum was. Okay. And what you'll find on this, I want to show you one other thing on our graph here. Let's do, I want to try to do this. I want to change this window and just kind of zoom around the 50. So you can watch this. You don't have to do this on your calculator if you don't want to. But I'm just going to kind of look at like maybe 40 to 60. And then I'm going to make this y, I'm going to change that max to like, I don't know, like 10 or something like that. Okay, just watch this because I want you to see something on this. So I'm zooming in around that minimum. Okay, and what's going to happen is you're going to see, first thing you're going to see is you should see the cost function coming out. Where is it? Oh, I think it's, I made my window go too small on y. Let's make that go to 100. And maybe scale that by 10. So I'm just kind of zooming in around where that minimum is. That's what I want you to see. Okay, so what happens on this, notice that at the minimum, which is right here, this is 50 right here. Well, notice that the marginal has the same y value, okay, but the oblique asymptote is different. So the idea is they're fairly close to each other, but if I trace at 50, which is our minimum, that thing is tangential to that right there. Okay, that's the idea. Okay, so that's how you would approach that problem, and I'm just trying to show you that the marginal cost is going to approximate the minimum average cost. That's the idea. Does that make any sense? Okay, yes, no? Okay, everybody good with what I did on that? I tell you guys are getting the oblique asymptote down. That's not very hard. And the derivative on that wasn't too hard either. Okay, so that'll wrap that up. Let's go ahead and start in